we said that a tree on n vertices is a graph that has these three properties. So a graph is a tree if, first of all, it is connected, and secondly, it has exactly n-1 edges, and finally, it has no cycles. Okay, and we saw in the last session that any graph that has two of these properties will definitely have the third property as well. So if you want to check if a graph is a tree, you can just check two of these. You don't have to check all three. Okay. So we want to prove some things about trees. First of all, I want to define the concept of a leaf, because I mean, of course, we're talking about trees, so we can also talk about leaves. So a leaf is just a vertex of degree 1. Okay. So if I have a vertex, let's call it L because it's a leaf, and it's only connected to another vertex, let's call that one U. Then I'll say that L is a leaf. In this case, in this very simple graph, both L and U are leaves, but I can have something like this. My graph does not have to be a tree. And then here only L is a leaf. Okay. So whenever I say leaf, I just mean degree 1, and it doesn't have to be in a tree, but usually we talk about leaves in a tree. Okay. So here's the first theorem for this session. I want you to prove that every tree has at least 2 leaves, but of course it should have 2 vertices to have 2 leaves. So every tree on n vertices, where n is at least 2, has at least 2 leaves. Okay. So if I want to draw some trees here, here's a binary tree, which you will see a lot, especially in 3711. Here's just another tree. But the important point is that, as you can see, the theorem holds. Actually, these trees have much more than 2. So here I have 4 leaves. Here I have 1, 2, 3, 4, 5 leaves. So I want you to prove that every tree has at least 2 leaves, assuming that it has enough vertices. Of course, the tree on one vertex cannot have 2 leaves, but if it has at least 2 vertices, then it has at least 2 leaves. Okay. Why is this the case? Now, one way you can prove it is using the same technique that we've seen last time, which is I start with an empty graph and I keep adding the edges one by one. Okay, but I'm not going to do that. I'm going to do something else. I want to give you the proof based on a maximal path. Or actually, I can even say, look at one of the longest paths. Again, it's not unique, so I cannot say look at the longest path, but I can say take one of the possible longest paths. So let's call it P, which starts at some V0, goes to V1, so on to Vk. I'm only writing the vertices here because you know the edges when I write the vertices, okay? So let this be a longest path of my tree. Okay. I claim that both endpoints of this path are definitely leaves. So I claim that V0 and Vk are leaves. Okay. Let's see. So for example, in this graph here, the longest path I can find is a path of length 4. And there are many such paths, but let's say I take this one. You see both endpoints are leaves. Okay. Now, let's try to prove this by contradiction. suppose that I have this path, and again, this is my longest path, so it starts at V0, goes to V1, keeps going until it gets to Vk minus 1 and Vk. Okay. Suppose that V0 and Vk are not leaves. What does that mean? If V0 is not a leaf, then that means that the degree of V0 should be more than 1, right? So there should be another edge coming out of V0. But where does that edge go? It cannot go to somewhere else in the same path, because if that happens, I have a cycle, right? And I'm talking about a tree. A tree doesn't have a cycle. So this other edge that is coming out of V0 has to go somewhere else, to a vertex that is not already in my path. But that gives me a longer path. I can just add this vertex to the beginning of my path, and I get a longer path. So this is a contradiction with the assumption that this was a longest path. I can say the exact same thing on the other end of my path. So look at Vk. If Vk is not a leaf, there should be another edge coming out of Vk. But that edge cannot go to anywhere inside my path, because if it does, then I will have a cycle here. So it will have to go to a vertex outside of the path, and now this is again giving me a longer path. So it's exactly the same argument on both sides. So whenever I have one of my longest paths, both of the endpoints, both V0 and Vk, have to be leaves. Okay? So great, I have two leaves. I have V0 and Vk. Now, let's do some counting. I want to ask you this. Suppose that I have a graph G, and my set of vertices is just the numbers from 1 to n. So I have n vertices. How many different graphs can I create on these n vertices? How many graphs G, V, E exist? Yes, 2 to the power of n choose 2. Look, if I have only two vertices, let's say 1 and 2, then I can look at this pair, and either I put an edge there or I don't put an edge there. So I will have only two possibilities. But in general, if I have n vertices, I can look at every pair. I can look at this pair, I can look at this one, all of them. And for every pair of vertices, I can decide whether I want to put an edge there or not. So how many pairs of vertices do I have? N choose 2. So I'm going to make n choose 2 decisions. And for each decision, I have two possibilities. I can either put the edge or not put the edge. So the total number of phase is 2 to the power of n choose 2. Or another way of looking at this is that consider the complete graph. The graph that has all the possible edges. It has n choose 2 edges. And any other graph is going to be a subgraph of my complete graph, where I have the same set of vertices, but I have to choose a subset of the edges. So if I have a set of this size, how many subsets does it have? 2 to the power of the size of the set. Okay. So, you know, whenever I ask you an easy question, I want to follow up with a hard question. So here's my next question. How many of the graphs in the previous problem are trees? So if I have n vertices numbered from 1 to n, how many trees can I create on these n vertices? Now, this is one of the nicest proofs of double counting that I've ever seen in my life. I love this proof. The answer is actually n to the power of n minus 2. Okay. And you will not believe how this is going to go. So I'm going to give you the proof. So basically, I want to encode every one of my trees as a sequence of lengths n minus 2 of the numbers from 1 to n. And I want to create a one-to-one correspondence. So I want to be able to translate every tree to a sequence, and I want this to be reversible. I want to be able to, again, translate every sequence back to the same tree. So here's how I create my sequences. So let's say I have a tree. I'm going to just create a tree here. And I'm going to number my vertices. So whatever, 1, 2, let's say this is 3, this is 4, this is 5, this is 6, this is 7. Okay. Now I want to write this as a sequence. And here's the rule that I use. Here's the algorithm that I use. Every time I look at my leaves and I find the leaf with the smallest number. Okay. So in this case, my leaves are 2, 4, 6, and 7. I find the leaf with the smallest number, which is 2. And then I write the name of its neighbor. Okay, so I find the leaf with the smallest number, that's 2. Its neighbor is 5. And then I remove this leaf from my tree. And I keep doing the same thing. Again, I look at all of my leaves. I have 4, 6, and 7. The smallest one is 4. Its neighbor is 1. So I write 1 and I remove 4 from the tree. Now, because I've removed 4, 1 is a leaf. So my leaves are 1, 6, and 7. The leaf with the smallest number is 1. Its neighbor is 3. So I'm going to write 3 and I'm going to remove this leaf. Now my leaves are 3, 6, and 7. It looks a bit weird, but 3 now has degree 1, so 3 is a leaf. So I have 3, 6, and 7. The smallest leaf is 3. Its neighbor is 5. So I write 5, and I remove 3. My leaves are 6 and 7. The smallest leaf is 6. Its neighbor is 5. So I write 5, and I remove 6. And basically, I continue this until my tree is just one edge. And when it's just one edge, I stop. So this is the translation. I translated this tree to this sequence. Okay. So did you all understand the algorithm for the translation? Very easy. Every time, take the leaf with the smallest number, write the name of its neighbor, remove this leaf, and keep doing this until you have only one edge. Okay. Great. Now I say, if someone gives me this sequence, I can translate it back to a tree. Okay. First of all, if I look at this sequence, based on this sequence, can I know which vertices were leaves in my original tree? Yes. All the vertices that don't appear in this sequence are exactly the vertices that were leaves in my original tree, right? Because if you're a vertex that is not originally a leaf, you will not be removed until all of your neighbors are removed one by one. So when one of your neighbors is a leaf and gets removed, I write your number in here, right? But if you're originally a leaf, your number will never be written here. So if I know that I have 7 vertices, which I know right now, I can just write all of my vertices, 3, 4, 5, 6, and 7. And initially, I know which vertices are the leaves. Any vertex that doesn't appear here. So 1 appears, 2 doesn't appear, 3 appears, 4 doesn't appear, 5 appears, 6 doesn't appear, and 7 doesn't appear. So just by looking at this sequence, I know that whatever tree is being explained here, 2, 4, 6, and 7 are going to be its leaves, just exactly what we had there. So I've at least found out which vertices are the leaves. Okay, but what was the rule here? When I wrote the first letter, I said that I look at the smallest leaf and I write its neighbor. So I know the leaves, I know that the smallest leaf is 2, and the sequence is telling me that its neighbor is 5. So I know that I have the edge 2, 5 in my tree. So far I have this. I know that I have the edge 2, 5. Okay. But now I can continue this. So I had this edge 2, 5 in my tree when I was doing this. So then I removed 2 and I wrote 5. So I can now remove this, and this part is going to represent the rest of my tree. Okay. Now, again, and 2 is already done. So now 4 is the smallest leaf. And from here, I know that 4 is connected to 1. So I could reconstruct this edge, 4, 1. Okay. So I remove 4 from here and I remove 1 from here. But interestingly, I don't have another 1 in the remainder of my sequence. So now 1 has become a leaf. Right. So now I know that 1 was connected to 3. So I know that I have this edge. I remove 1, I remove this 3 from here. I don't have any more 3s. I know that 3 has become a leaf. My smallest leaf is 3. It says it's connected to 5. So I found this edge. I remove this, I remove this. My smallest leaf is 6. It says it's connected to 5. Okay. So I found this edge. I remove this, I remove this. Now 5 becomes a leaf. So now I have only 2 remaining vertices and they're both leaves, so they should be connected to each other. So 5 should be connected to 7 as well. And as you see, I could basically reconstruct the exact same tree. And this process works for any tree. You can check this, right? I'm not going to formally prove it, but it's not that hard to prove. So I took a tree and I translated it to a sequence of length n minus 2. Because remember, I'm writing these numbers until I have only 2 vertices remaining, and then I stop writing. Okay. Now, if you give me any sequence of length n minus 2 of my numbers, I can also translate it to a tree. There is no case where my translation fails. So the number of trees is equal to the number of these sequences. And I have a sequence of length n minus 2. In each of the places, I have n choices for what number to write. So I have n to the power of n minus 2 such numbers, such sequences. So the total number of trees is n to the power of n minus 2. Okay. Great. Now, as a homework, we say a graph is a forest if it's not necessarily connected, but if every connected component is a tree. So a forest is a collection of disconnected trees. Try to count how many forests we have on n vertices. Now, let's go and let's prove some other theorems. I want you to prove this theorem. Let's say that I have a simple graph, and let's say it has at least 2 vertices. I want you to prove that it has at least 2 non-cut vertices. So every graph with n greater than or equal to 2 vertices has at least 2 non-cut vertices. Let's say every connected graph. Okay, so if I give you a graph and it's already connected, as we talked about last time, a vertex is called a cut if removing that vertex makes your graph disconnected, if it increases the number of connected components. I'm saying every graph has at least 2 vertices that are not cut. And again, of course, we're talking about simple graphs. We always talk about simple. Okay. Now, the idea here is actually quite similar to this one, right? Because if you think about it, a leaf can never be a cut vertex. A leaf has degree 1. So if I remove a leaf from a connected graph, it's never going to get disconnected, right? But this was in trees. In trees, I could say that I have at least 2 leaves. Now I'm saying in general, if I have a connected graph, I might not have any leaves at all. Maybe I have a complete graph. Everything is connected to everything. Everything has high degree. But I'm definitely going to have at least two non-cut vertices. Okay. Let's do exactly the same thing that we did in the previous theorem. Let's look at a longest path. Now, very importantly, I cannot say let's look at the longest walk, because in walks I can repeat edges and I can repeat vertices, so I might have an infinite walk, right? But when I'm talking about paths, I know that the length of my path is at most n-1, because the length of the path was the number of edges in it, and I can see at most n vertices, and I cannot repeat any vertex, so the length of a path is at most n-1. So I can say, look at a path with maximum lengths. So let P, again, I'm going to call it V0, V1 to Vk, be a longest path. Okay. Now, just as before, I want to claim that the two endpoints of this path cannot be cuts. Okay, so I claim that V0 and Vk are not cuts. Okay. Let's just draw it again as before. So I have V0, I have an edge that goes to V1, that goes to V2 maybe, so on. And at some point, I'm getting to Vk. Okay. What can I say about V0? What can I say about the neighbors of V0? So every neighbor of V0 has to already be in this path. Because if V0 has a neighbor that is not in this path, I can add it to this path and I can get a longer path. So V0 might have a lot of edges coming out of it, but all of those edges are connecting it to other vertices in the same path. And I can say the same thing for Vk. If Vk has a neighbor that is outside of this path, I'll get a longer path. So all the neighbors of Vk are also in the same path. Okay. So now, why would removing V0 not change the number of connected components? Because look, if V0 was supposed to be a cut, when I remove V0, there should be two neighbors of V0 that cannot reach each other anymore, right? But all the neighbors of V0 are already in this path. So even if I remove V0, they can definitely reach each other. All of these are connected to each other. So V0 is not a cut vertex. Now, the argument for Vk is exactly the same. It's just like the mirror image of V0. All of its neighbors are in this path. So if I remove Vk, all of its neighbors can still reach each other. So if my graph was connected before, it's going to be connected after. So both V0 and Vk are definitely not cuts. So I have two vertices that are not cuts. Okay. Let's do another theorem. I want to say this. I want to say, suppose that I have an odd walk. So I have a walk whose length is odd. Okay. I want to say that it definitely contains an odd cycle. Okay. So this is what I want to say. Every odd walk contains an odd cycle. And again, whenever, not odd walk, odd closed walk. It has to go back to where it starts. Right? So let's say I start from some vertex, I take an odd number of steps, and maybe I see some vertices and edges several times, but I go back to where I started. I'm claiming that I can find an odd cycle in there. So I can make it so that I don't see any vertex more than once except for the initial vertex. Okay. So let's try to prove this. let's say I have my odd VOC, and let's say that my VOC is a set of vertices. So let's call it V0, V1, V2, so on to Vk. This is a sequence of vertices. And first of all, I just check, is my closed VOC, actually this Vk is the same as V0. Right? So I first check, is my closed VOC already a cycle? If it is a cycle, I'm happy. I don't have to do anything. I found my solution, right? Otherwise, if it's not a cycle, it means that there is some I and j such that I is not equal to j, but Vi is equal to Vj. Okay. And also, I'm not going to consider the corner case where I is 0, because if I is 0, like I'm starting at V0 and I'm getting back to V0 at some point, now I have a smaller closed VOC, and then I can keep doing the same thing. Right. But basically, this means that I'm starting somewhere at V0, I'm going somewhere, and then at some point, I'm going back and crossing myself. So this is Vi, which is the same as Vj, right? And then I'm going somewhere else, maybe crossing myself a few more times until I'm getting to Vk. And remember, this Vk was the same as V. Okay, so maybe instead of drawing it like that, oh, no. Instead of drawing it like that, let's say I go back to V0. So this is my closed VOC, and I know that it's odd. So I know that the total number of edges is odd. Okay. Now, look at this part here. This is also a closed VOC, right? Okay. So I have my big closed VOC, and I could actually divide it in two smaller closed VOCs. One is that, one is this part. Oh, I regret this now. Okay. So I have the blue part and I have the red part. But the total number of edges was odd. So either the blue part is odd or the red part is odd. Whichever is odd, I take it and I continue doing the same process on it, right? So this process cannot go on forever because of infinite descent, because my number of edges is going down every time. So at some point, I get to an odd closed VOC where I don't have any repeated vertices in between, where I cannot have something like this, right? And when that happens, that's a cycle. And it's an odd cycle because every time I'm choosing the odd part. So every time that I'm dividing my big VOC into two smaller VOCs, I'm saying, if the blue part is odd, continue with the blue part. If the red part is odd, continue with the red part. So I'm always keeping it odd, but I'm also decreasing the size. It cannot decrease forever. It has to stop at some point. The only case that this will stop is if I have an odd cycle. So every odd closed VOC contains an odd cycle. By the way, almost all of these theorems are also in the book. And in almost all of the cases, the proof that the book gives is different than my proof because I just make it up as I'm going. Okay. Now, I want to define the concept of a bipartite graph. Okay. I say that a graph G, let's call it VE, is bipartite. Basically, it means that it has two parts. If I can take my set of vertices and I can divide it into two separate parts, V1 and V2. So this means disjoint union. So it means that V1 and V2 have nothing in common. There's no vertex in both of them. And my set of vertices is just V1 union with V2, okay? So my graph is bipartite if I can divide my set of vertices into two different sets such that every edge goes from the first set to the second set, such that every edge has one endpoint in V1 and one in V2. Okay. So for example, suppose that I have this set of vertices. Let's say these are the vertices in my V1. These are the vertices in my V2. Every edge goes between the two parts, right? So I have something like this. There is no edge that has both of its endpoints in V1. This is not allowed. There's also no edge that has both of its endpoints in V2. This is also not allowed. So I say a graph is bipartite if I can divide the set of vertices into two sets such that every edge goes from the first set to the second set. Okay. Now I want you to prove this famous theorem. A graph G is bipartite if and only if it has no odd cycles. Okay. So if you look at this graph here, I actually drew a graph that has no cycles at all. So it's bipartite, which by the way means that all of the trees are definitely bipartite, right? Because a tree is a graph that has no cycle. And I'm saying a graph G is bipartite if and only if it has no odd cycles. So I'm even allowing even cycles. But okay, let's make this have a cycle. So I can do something like this, and I can do something like this. Does it have a cycle now? Yes. So I have this cycle going up there, down here, here, and back. Okay. But it's a cycle of length 4. So it's an even cycle. I claim that I cannot have an odd cycle. Basically, I'm saying the graph is bipartite if and only if it has no odd cycles. Okay. Let's try to prove this. Which side do you want to start first? Because this is if and only if. Do you want to assume the graph is bipartite, or do you want to assume the graph has no odd cycles? Let's assume the graph is bipartite. Let's do this part first. So I want to say if the graph is bipartite, then it has no odd cycles. Okay. So here's the thing. Suppose my graph is bipartite. Okay. And let's say I start at a vertex in V1. Okay. When I take one edge, I will go to a vertex in V2. Because we said that all of the vertices go between the two sides. So if I have some vertex X in V1, and I start at X and take one edge, I will be in V2. And then from there, if I take another edge, I will go back to V1. If I take another edge, I will go back to V2. Now, you see the issue here. So whenever I take an odd number of edges, I end up in V2. Whenever I take an even number of edges, I'm back in V1. So if I have an odd cycle, what does it mean? It means that I started at X and I took I started at X, I took an odd number of edges and I'm back at X. But that doesn't work because my graph was bipartite. And I said that if I take an odd number of edges, I will end up in the other part. I will end up in V2. Mm-hmm. So if my graph is bipartite, it has no odd cycles. By the way, great figures, as you see. The TAs are going to have a really hard time writing the notes for this one. Okay, now let's do this side. So now we're assuming that our graph G has no odd cycle. Okay, And assuming that it has no odd cycle, we want to prove that it's bipartite. So we want to somehow divide the vertices in two groups. How would you divide the vertices in two groups? Well, let's just start with an arbitrary vertex, and let's say I want to have two groups, right? I want to have V1 here, and I want to have V2 here. So let's say I pick one vertex, pick your favorite vertex, whichever you want, and put it in V1. So let's say I put vertex X in V1. Okay. Now, if X is in V1, I have to put all of the neighbors of X in V2. So I look at all the neighbors of X, and I put all of those in V2. But now, if I put some vertices in V2, I have to put all of their neighbors back in V1, right? So I take all of the neighbors of the vertices that I had in V2, and I put them in V1. And I keep doing this. At every step, I'm just finding new vertices, and I'm adding them to either V1 or V2, okay? This goes on until I add all the vertices that were in the same connected component as X to either one of the two sides, right? Because of course, with this process of going X from X to its neighbors and then neighbors, and so on, I'm just going to see the connected component of X, right? So I'm not touching anything outside of the connected component of X, but everything in the connected component of X is put either in V1 or in V2. Now, the question is, will I ever reach a case where I have a problem? So you see, I put X here, then I put its neighbors in V2, okay? Then I'm saying, take the neighbors of these neighbors and put them in V1. But can these neighbors of neighbors also be neighbors of X? Can I have an edge like this? No, because that creates an odd cycle, right? And because I don't have odd cycles, I will actually never run into a problem. So first, I'm putting X in V1, then I'm putting all the vertices that were at a distance of one edge from X in V2. Then I'm putting all the vertices that were at a distance of two edges from X in V1. Then all the vertices that were three edges apart in V2, and so on. But if I have a vertex, let's say I have some vertex Y, I'm saying that it's either going to go in V2 or going to go in V1. So I'm saying that if I start at X, any walk that goes to Y is either, I either have this case where all the walks that go to Y are odd, or all the walks that go to Y are even. That's what I'm claiming, right? Because that means that I will never have a problem here. That means that every vertex Y will either get added to V1 or V2 based on whether all the walks from X to Y are even or all of them are odd. Now, suppose this is not the case. Suppose I have a walk from X to Y that is odd, and I have another walk from X to Y that is even. If I add these two walks together, I get a closed walk, and that closed walk is odd. But we said that if we have an odd closed walk, then we have an odd cycle. And we know that we don't have an odd cycle, so I cannot have anything like this. So when I have my vertex X, for every other vertex Y that is in the same connected components as X, either all of the walks from X to Y are odd, or all of the walks from X to Y are even. If they are odd, I add Y to V2. If they're even, I add Y to V1. Okay, but this only works for one connected component, right? I've only decided what to do with the vertices that were in the connected component of X. Just do this for all of the connected components. Just pick your favorite X, you cover its connected component. Then in the next connected component, pick another favorite X, put it in V1, do the same thing, right? This divides your graph into two parts, and there are no edges that have both of their endpoints in the same part. So if G has no odd cycle, then G is bipartite. Okay, let's do another one. This is another theorem. I want to say, suppose that I have a graph G, and this graph has no leaves. So the degree of every vertex is at least 2. It doesn't have leaves. It doesn't have vertices of degree 0 either. So let's say, assume the degree of vertex I is at least 2 for every vertex I that is in my set of vertices. Okay. I want you to prove that this graph G has a cycle. Okay, so I have a graph G, and in this graph G, the degree of every vertex is at least 2. You have to prove that it has a cycle. You can actually use some of the previous theorems that we had. So yeah, let's look at this graph. Let's look at my graph G. It's not necessarily connected. So I can say that G has several different connected components. Okay, let's call these connected components C1, C2, blah, blah, to CK. Right? If G has no cycle, then each of these connected components should be a tree. Right? But we just talked about this. If I have a tree, and if this tree has 2 vertices, then it's definitely going to have 2 leaves as well. But I cannot have any leaves. Right? So the only remaining case is that these trees have only 1 vertex each. But if you have 1 vertex, then the degree of that vertex is 0. Right? So that's also not possible. So if the degree of every vertex is at least 2, at least one of these connected components is not going to be a tree. Actually, none of them are going to be trees. And so there is a cycle in every one of your connected components. Okay. But can we prove this without going back and talking about trees? Can we actually just create the cycle? Again, I can do an argument similar to some of the previous theorems. I can say, look at one of the longest paths. So I can say, let V0, V1 to Vk be a longest path in G. Okay. What does this mean? Again, I'm going to just draw it. I have V0, V1, so on to Vk. Now, I have this assumption that the degree of every vertex is at least 2. So that applies to V0 as well. So vertex 0 has to have an edge going out of it other than the edge to V1, right? So I have an edge going out. This edge cannot be to a vertex that is outside of this path, because that gives me a longer path. So this edge goes to somewhere inside this path, but that gives me a cycle. This is the cycle, right? So if every vertex has degree at least 2, I definitely have a cycle. Now, here's kind of the opposite scenario. So let's say that the degree of every vertex is at most 2. So in the graph G, we have that for every vertex I in the set of vertices, the degree of I is less than or equal to 2. Okay. I want you to prove that every connected component of G is either a cycle or a path. Okay. Prove that every connected component of G is either a cycle or a path. Okay. So for example, I can have a graph that looks like this, right? I have a path, I have a cycle, maybe I have another cycle. Maybe I have just one vertex on its own, because the vertex on its own is both a path and a cycle, right? So as you see, this is an example of a graph with 4 connected components. The degree of every vertex is at most 2. And every connected component is either a cycle or a path. Of course, this is not a proof, this is just an example. I want you to prove that any graph where the degree of every vertex is at most 2 has this property that each of its connected components is either a cycle or a path. Okay. So here's the thing. Suppose someone else has given me a graph G that satisfies this property, the degree of every vertex is at most 2. First of all, I say, if you have any vertex of degree 0 that is its own connected component, just remove that from the graph because, yeah, fine. This is a path and a cycle. I'm happy with that. Okay. Then I'm going to say, pick an arbitrary vertex. So pick an arbitrary vertex, let's say V in the set of vertices. And whenever I say pick an arbitrary vertex, I mean, I don't care how you pick it. Pick it randomly, pick vertex number 1, do whatever you want. Okay. So I picked the vertex V. Now, the degree of V cannot be 0 because I've already removed all the vertices with degree 0. Okay. So there is at least one edge going out of V. So I'm going to start a walk. I'm going to start at V, and I'm going to take the edge that goes out. If there are several edges, take whichever you like. Okay. I get to a new place. Let's call this one V1. Do the same thing. If there is another edge, just take that edge. Keep doing this. As long as you're not at a dead end, as long as where you are gives you another edge that you have not traversed before, just keep taking that edge. Okay. Now I'm in a finite graph. Oh, maybe I should have said that. In finite. Gee. Yeah, we will give an infinite example where this is not the case. So imagine if I have an infinite graph where I have one vertex for every integer, and then I has an edge to I plus 1 and I minus 1. Technically, that's a path. No, it's an infinite path. I don't know. Anyway, we're talking about finite graphs here. So I pick an arbitrary vertex V. I just start walking. I start at V, go to some other V1, keep going, V2, V3, until I get to a point where I cannot find any more edges. Okay. Now, when I get to this VK, it's possible that there is no other edge going out of VK, but it's also possible that there is an edge, but it's going back to one of the vertices that I've seen before. And because I want to create a path, that's why I didn't take that edge. Okay. Now, I look at this VK, and suppose that it has an edge that goes back to one of the vertices in my path. Okay. Would this be possible? Can VK, for example, have an edge to V2? No, because the degree of V2 becomes more than 2. It has 2 edges in the path, and now it has another edge. So if I ever go back to another vertex in the path, it has to be the first vertex. I will be forced to have this. Right? But in this case, I have a cycle. Right? So I just started at V, kept walking, I got a cycle. Now I claim that this cycle is all there is in its connected components. There is nothing outside of this cycle in the same connected components. Well, that's also easy. If you look at a cycle, every vertex in this cycle already has 2 edges. So none of these vertices in this cycle can have an edge to something outside. So this cycle, if I find the cycle, that cycle is definitely going to be its own connected component. Okay. But this was only in the case where I got lucky, where I found a cycle. But suppose that doesn't happen. So suppose I start at V, and I keep going, and I get stuck at some point. Again, I'm getting stuck because I have a finite graph. I cannot keep going forever, and I'm not going back to the same vertex. I'm creating a path. Okay, so let's say I got stuck at VK. If the degree of VK was 2, I know that it would already give me a cycle. So this is the case where I've got stuck at VK, and the degree of VK is 1. Okay, so I've already found a path. But I cannot necessarily say that this is the entirety of my connected components. So what I'm going to do is that now I'm going to walk in the opposite direction. I'm going to say, okay, I'm at VK, this is a dead end. Let's go back. Let's go back to V. And let's see if we can extend it from this side. Let's see if I have somewhere else to go from V. Let's say I can go to W1, W2, so on to WT. Okay. I will again get stuck at this side too, because it's a finite graph. But when I get stuck, this one will also have degree 1. Because if this one has degree 2, then I will have a cycle. I've already covered the case of the cycle. Okay, so now I have a path. And I claim that this path is, again, the entirety of my connected components. Now, what do I know already? I know that the degree of this endpoint is 1. I know that the degree of this endpoint is also 1, right? So I definitely know there are no edges coming out of VK except for the edge that was already in the path. And I know the same thing for this endpoint, WT. But if you look at all the other vertices, they already have 2 edges connected to them. So these other vertices can also not have any edges going out of them, because they already have consumed their budget of 2 edges. Their degree was at most 2. So this connected component is just this path. So you see, in a very algorithmic way, actually, I can either find a cycle. So I start at V, keep walking. If I get back to V, I found a cycle, I'm happy. If I get to a dead end, I go back to V, I try to walk in the other direction, and I get to the other dead end, and then I'm happy because I found the path. So in any case, importantly, this V was arbitrary. So wherever I start, I'm getting either a cycle or a path, and that's the connected component. So I remove that cycle or path, and then again, I continue the same thing. Pick a vertex arbitrarily, keep walking, find either a cycle or a path. And keep doing this until you cover your whole graph, until you find all the cycles and paths, which are all the connectors.